Welcome back for our next discussion in Chapter 9 of Calculus 2. We're continuing our journey in really series, but taking a little different twist. And if you remember in the last videos, we introduced this idea of Taylor polynomials. And so we're taking a function that's not a polynomial and approximating it by a polynomial centered at a certain point, right? We always have to have a center. Where are we starting from? And so you pick a point on the curve. You start with just the constant line at that point. So the value is the same as the value of the function at that point. And then we write the equation of the tangent line at that point. And that's something we do in Calc 1. And that's what we call the linear approximation of the function at that point. But now what we want to do is we want to extend that and start to warp that tangent line and start to turn it and curve it in a way so that it agrees for more and more time away from this point with my function. And so we're trying to warp my tangent line. We're giving the tangent line concavity or a second derivative. We're giving it third derivative, fourth derivative. We extend this process. We're warping this line to mold it to the curve, the function, and creating a polynomial that, again, approximates my function at that point and is a really good approximation for a good amount of time. And that's the goal. And we can write out the fourth degree Taylor polynomial, the fifth degree Taylor polynomial, right? We're going out to 5 derivatives or 4 derivatives. But really the goal would be to, can I extend this indefinitely? Can I create an infinite Taylor polynomial that agrees with my function for all time from that point, right? Starting at this point, can I warp it to fit this function for all time? And that's kind of what we're going to go off of today, because we're going to introduce what we call a power series. Now, a power series in general is of the form, right? We have an infinite sum. Notice it is starting at 0 instead of 1. We have some sort of coefficients here, okay? These are not a variable, right? X is my variable. That is the only variable in this function. N is my coefficients, you can think of them as. And x minus c, that would be a power series centered at c, where the polynomial power is centered, x minus c to the n. And so if you just write out this sum, this infinite series, right, what this means sum, when n is 0, we get anything to the 0 is 1, so we just get a0. When n is 1, we get a1, x minus c to the 1. When n is 2, we get a2, x minus c squared, and so on and so forth. And we see it is just an infinite polynomial. That is what a power series is, an infinite polynomial. The coefficients are these ai terms, and the center of this polynomial is at c, right? It's shifted horizontally to be centered at c. And so we call that a power series centered at c. Now, this should not be completely unfamiliar because this type of format, right, this construction looks very similar to how we constructed Taylor polynomials. In fact, Taylor's polynomials can be written as a power series. If we just extend that algorithm for Taylor polynomials and we just extend it indefinitely, infinitely, we can create what we call a power series for a Taylor polynomial. We'll call it a Taylor series. And so the coefficients here are just general AIs, and here they're very much prescribed, right? The way we constructed these Taylor polynomials, what were the coefficients in front of my polynomial terms? They were the nth derivative of a function centered at c, so the nth derivative evaluated at c over n factorial, and then my polynomial piece attached. And so if we write this out, right, we're getting the Taylor polynomial. If we stop at any point, that's the second degree Taylor polynomial, the first degree Taylor polynomial, the third degree if I want one more step out, and so on. But we can write it out infinitely and create what we call a Taylor series. Now, for an example of that, remember we worked with e to the x in the last video, and we constructed a Taylor polynomial for e to the x centered at 0. But if we actually extended that process indefinitely, and this is the easiest one to do because of the pattern, since we're centered at 0 and the derivative of e to the x is always e to the x, all we need to know what e to the 0 is, which is 1. And so actually all of these fn of c, right, these nth derivatives at c, the nth derivative at 0 in this case, is always going to be 1. Because it's always e to the 0. And so here, we're always going to get 1 in the numerator's constant. Over n factorial, x to the n, right? C is 0. And so we can write out an infinite Taylor polynomial, or a Taylor series for e to the x centered at 0. Now, really the question is, and this is where we're going to kind of try to answer in this video, is can I really say equals right now? Is e to the x actually equal to it? Because the idea of Taylor polynomials, it was an approximation. And when we looked at that visualization in the last video, you saw that even though it looks good for a decent amount of time, if I start to zoom out, then at some point that polynomial diverges from the curve, right? It doesn't agree with it anymore. And even though I went out infinitely, well, this curve extends forever. The domain of e to the x is all real numbers. Did I really get e to the x for all time? Is the domain of this polynomial match the domain of e to the x? Or is the domain of this polynomial only restricted in some range? And that's going to be kind of what we want to seek to answer. And so Taylor polynomials, Taylor series, this is kind of an extension of what we did in the last video, but what we're really concerned with right now is just power series in general. So power series in general don't have to have coefficients that come from some sort of function that you're approximating. In general, they can just have random coefficients. Again, we don't have to start with a function that we're approximating by a Taylor polynomial. We can just start out with a straight power series, an infinite polynomial. Now, in algebra class, anytime you define a new function, anytime you bring a new function, you always want to know, okay, what am I allowed to plug into this function? What is the domain of the function? Now, if you remember what domain is the allowable input. What am I allowed to plug in? What values of x, remember the variable is x, not n, what values of x will give me outputs? Well, plugging in certain values of x will create an infinite series for you. And so it's not necessarily as easy as saying input output, because really the question is, for what values of x will the series that's created converge? We're going to create a series, right? Replacing x with some number. Now I just have an infinite series. And now the question is, does that series converge? Does it give me a finite number back? Does it give me an output? And so we can rephrase the what is the domain question to this question. For what values of x does the series converge? Now, domain is typically given in terms of an interval. If you remember in algebra class, intervals of domain, interval notation. And so we're going to mimic that here. We're going to write our answers in intervals, the values of x for which the series converges. That's an interval. And instead of calling it the domain, we're just going to call it the interval of convergence. You want to find the interval of convergence. Find the interval of convergence. Now, of course, in order to know a domain, it would be good to have a place to start. And fortunately for us, there is one value of x that right away we can plug in directly and know that the series converges for that value of x. And it goes back to the reason why we call this a power series centered at C. For example, if you look here, not for example, in this general case, if you let x be C, what is f of c? Well, that's a series replacing x with c. We get a-n, 0 to the n. And so if I write this out, this infinite polynomial, remember what we get here. If we're just replacing x with c, then the only thing that will remain is a0, the first term here. And you might be wondering, but yes, 0 to the 0 is 1. Weird. A0 here. That's a finite number. It's just whatever the first term is, right? If you write out this infinite polynomial, and I ask you to replace every x with c, then all the polynomial terms disappear, all the power terms disappear, leaving me only with a0. And so right away, based on this, we know that we converge at c. So the series converges at x equals c. And so for that reason, we're going to call C the center of convergence. It's the center of my power series, centered at C. We're going to call it the center of convergence. And oftentimes you'll see this as where is the power series centered? And what do they mean by that? They mean the center of convergence. So C is the center of convergence. And so I know that I can plug in C. Outside of that, I have no idea. And so now how are we going to move away from C? Well, we're just going to take a little step at a time. And so how do we find the interval of convergence? It's going to come down to asking ourselves, how far can we move away from C in either direction? I want to move both directions away from C. C is somewhere on the number line. We want to move a little behind it, a little above it. How far can we move away from x equals c in either direction and still converge? That's the question. Well, the distance we can move away from C is called the radius of convergence. So the distance we can move away from C and still converge is called the radius of convergence. Radius of convergence. And we're going to call this R. Use capital R for the radius of convergence. And so you imagine C on the number line somewhere, right? It's a value which you know you can plug into this infinite polynomial. And we need to ask ourselves, how far can I move away from C in either direction and still get something finite back, still converge? Now that we know what we want to do, right? We want to find how far away we can move from C, giving me some sort of interval in which we converge, the interval of convergence. What are the possible situations for R? It's going to be our question. How far can I move away? What cases do I run into? And so there are three cases for the value of R. So the possible values of R fall into three categories. The first case is the most boring case, and that is that R is 0. What that means is you can't move away from C at all. The series converges at C and only C. And if you try to move away from C in any direction, as small as you would like, you would diverge. That series would blow up and not give you anything finite back. And so the domain of the function is very boring. It's a single point, C and C itself. And that's it. The other extreme would be that R is infinite. What that means is I can move as far away from that center as I like, and it would still converge, meaning the domain is all real numbers. So in the first case, the domain is just C. In the second case, the domain is all real numbers. Those are the two extremes. And just like Goldilocks, right, the one that's right in the middle would be the most interesting case, and that's the case where you get some sort of finite positive number. That you have a certain fixed distance that you can move away from C. And as long as you're inside this interval, you converge, and once you're outside this interval, you diverge. And so the domain of that power series is limited to some sort of interval, some sort of finite length interval. And so if R is 0, what does this imply? This implies that the interval of convergence is just a single point C. It's not even an interval, it's just C itself. What does this imply? If R is infinity, the interval of convergence is all real numbers, negative infinity to infinity. And the last case, R is finite and positive. This implies that the interval of convergence looks something like this. C minus R to C plus R. Because this is the case where, and I'll draw the number line, you have C, that's the value for which you converge. You have some sort of distance that you can move away on either side, R here. And so where does that put me here? C minus R and C plus R. Moving away from C, a distance of R. And really, the other question we have, and we don't know this, and we're going to have to answer this, is since it is a finite interval, should we have brackets or parentheses? We don't know yet. They could be brackets, they could be parentheses, one could be a bracket, the other a parenthesis, vice versa. And so this is the most interesting case. These are the three cases for what R could be. So either it's C itself, it's all real numbers, or it's some sort of finite interval. Now, how do we find it is going to be the question. How do we find the domain or the interval of convergence? How do we find this distance we can move away from the center? So how to find the radius and interval of convergence. Well, we're dealing with a series. Now, fortunately for us, we just spend the good part at the beginning of chapter 9 and the most of chapter 9 through 9.6 talking about testing for convergence of a series. And so I would like to know when the series converges. For what values of x does the series converge? I'm going to use a convergence test for series. And the convergence test I will use will be one of two. We will use the ratio or root test. Ratio or root test. Why the ratio or root test? Because of course you notice, what does a power series look like? Well, by definition or by construction, it's definitely an nth power, x minus c to the n. And so the ratio or root test would be great for this nth power. In the Taylor polynomial case, remember that this had a factorial in it. And so the ratio test would be great, or the only test really that I could use. And if it doesn't have a factorial, well then maybe the root test if I can take an nth root of it. And so the ratio or root tests are going to be one way to go for us to test the interval and radius of convergence. There's two reasons. One is just because of the construction of how a power series looks. The other reason is because remember the radius or the ratio and root test, they test for absolute convergence. Meaning I'm taking absolute values. Why do I care about that? Because if I have the absolute value of something, absolute value is a two-sided inequality. So recall absolute value, how absolute value works. If you have some sort of statement, for example, like the absolute value of x is less than 2, that doesn't just mean x is less than 2. That means x is less than 2 or greater than negative 2. It means on the number line centered at 0, you have this interval between negative 2 and 2. Even if I move it, if I say something like this, x minus 1 is less than 3, that doesn't mean that x minus 1 is just less than 3. That's two-sided. It means x minus 1 is less than 3 or greater than negative 3 because its value is less than 3. So if I just add 1 to everything, that gives me 4 on this side, negative 2 on this side. I add 1. That gives me now an interval. Now, we can do this, or we can just think of it as this is a expression centered at 1, representing the distance away from 1. 1 is the center. How far can I move away from 1? What's the value of this distance? Less than 3. And so I can move 3 steps this way or 3 steps this way. That puts me up to 4, and moving 3 steps backward puts me down to negative 2. And so just like before, we get some sort of interval here. So we care about this because not only is it a good test to use just because of the construction of a power series, how it looks, it's also a good test to use because it will tell me then how far can I move away from C in either direction. It'll give me a two-sided inequality. It'll give me both ends of this interval away from C. And so for that reason, when we test to find the radius and interval convergence, we will limit ourselves to using the ratio and the root test. And so this was the setup. This is the kind of the idea behind what a power series is. The main question that we want to find, i.e. the interval of convergence. And then in the next video, what we'll do is we'll do examples. We'll write up some power series and find those domains, find that interval of convergence and that radius of convergence and answer those questions.